Hello, and welcome back. Recently, I've been working on a series about the mathematics behind the most important operator in all of science and mathematics, the Fourier Transform. Last time, I gave a proof that the Hermite functions were actually eigenfunctions for the Fourier Transform, and since they are also an orthonormal basis for L2, this means that the world's favorite operator is diagonalizable over L2. The proof that I presented was slick, and honestly, it was beautiful. It leveraged our knowledge of the Fourier transform of the Gaussian and the fact that the Gaussian is the generating function for the Hermite functions. Ignoring one or two mistakes I made on the board, it gives a complete picture in only one board of work. But there was one problem. The proof was slick. Too slick, to be honest. It felt like a proof coming out of Walter Rudin's textbook Principles for Mathematical Analysis. It was quick, to the point, and it solved the problem. It also is completely opaque to anyone first learning about the Fourier transform. One viewer made a remark likening our process to finding eigenvectors for a matrix, which gave me an idea. Could I make a video discovering the eigenfunctions of the Fourier transform numerically, without knowing that the Hermite functions are actually the eigenfunctions we're looking for? So this video is going to start with a couple of simple concepts we can glean from the Fourier transform's definition, and we're going to set ourselves up to make a MATLAB routine that discovers the diagonalization of the Fourier transform. This is going to brush up against many interesting concepts in operator theory, such as invariant subspaces for an operator, the spectrum of an operator, orthogonalization and the Graham-Schmidt algorithm, and computing inner products in MATLAB. Most of what we're going to do is typical linear algebra and calculus. We're going to talk about inner products, we're going to use integration by parts, and changing the order of integration. And at the end of the day, we're going to have an orthonormal set of functions spat out by our code in MATLAB, which we'll compare to the Hermite functions, which we have already discovered in a series of lectures on this channel. So let's get to the board and talk about what we're going to do today. Okay, so this video has been taking a lot longer for me to make than I thought. I've had to re-record a lot of things, so my hair's changing, my shirts are changing. This just recorded over like 3 or 4 weeks, maybe even a month at this point. In any case, so this is a bit of a long video, but let's outline some of what's coming up. The first big step here is to convert the Fourier transform over L2 to a matrix. This involves selecting some basis elements in L2 and seeing if we can describe the action of the Fourier transform on those basis elements in terms of that same basis. If we can, it gives us hope of finding eigenfunctions. Once we have the eigenfunctions, we want to then orthogonalize them to get the Hermite functions. This means we are going to have to also talk about the Graham-Schmidt process and how to take an inner product in L2 according to the basis we have selected. The basis we will select is x to the n times the Gaussian. There are actually several reasons for this. First, we know that these are all in L2. They actually also serve as a basis for L2, but that would take a little bit too much time to explain. So I'll save that for a future video. Second, we know the Fourier transform of the Gaussian is also a Gaussian, which gives us a starting point for figuring out the Fourier transform of the other basis functions by exploiting this property of the Fourier transform. That is, the Fourier transform of x times the function f of x is I times the derivative with respect to w of the Fourier transform of f of x. This is a really nice formula that we worked out a couple videos ago. So we can get from the Fourier transform of a Gaussian to the Fourier transform of x times Gaussian by this operation. This happens to give negative I times w times the Gaussian. Now, we just have happened to have found two eigenfunctions for the Fourier transform right here. One with eigenvalue 1 and another with an eigenvalue of minus I. But that's not going to happen every time we do this. Now, if we do this again, we get the Fourier transform of x squared times the Gaussian actually is this. Now we can notice that the Fourier transform is leaving the space of quadratic polynomials times the Gaussian invariant. What that means is if we make a matrix from these three results, then that gives us a complete description of the Fourier transform on this subspace of L2. And any eigenfunctions or eigenvalues we find this way will be eigenfunctions and eigenvalues for the full Fourier transform. And so, with that in mind, this is the matrix we get. Note that this matrix is upper triangular, which means that the values along the diagonal are actually all eigenvalues for the Fourier transform, and not just for this matrix. Now, let's figure out how to do this for all x to the n times the Gaussian, or all of our basis elements.
So what we're going to do is we're going to go ahead and cook up some sort of recursion to go from this to the next one. And then we'll be able to input that directly into MATLAB, and using the symbolic toolbox, we'll be able to spit out a whole bunch of nice coefficients for the matrices that we want to make. So let's go ahead and take a look. All right, so we'll say the Fourier transform of x to the n times e to the minus x squared over 2 is equal to some polynomial with regards to w times e to the minus w squared over 2. Now we know this inductively, this works because we've seen this for the cases of n equals 0, 1, and 2. And so now we're just going to go ahead and show that when you start with this guy, giving you a polynomial times Gaussian is always going to give you another polynomial times Gaussian, and then that's going to give us the answers that we want. So let's go ahead and take a look. So if we want to have the Fourier transform now of x to the n plus 1 times e to the minus x squared over 2, this is going to be equal to I times d by dw of pnw times e to the minus w squared over 2. So now let's go ahead and Jill, take the derivatives and multiply it times I. It's actually not that too bad. So this is going to end up giving us that Pn plus 1 of w is equal to I times Pn prime of w minus w Pn of w. And so we see that Pn plus 1 is going to be an n plus 1 polynomial, and that also tells us that we have these invariant subspaces that we're talking about. The polynomials of degree n times the Gaussian are mapped to polynomials of degree n times the Gaussian by the Fourier transform, which is pretty nice. Okay, so this gives us now the tools to jump into the symbolic toolbox so that we can go ahead and make our matrix representations of the Fourier transform. And we know that they're all going to be upper triangular matrices, so the diagonal is going to give us these eigenvalues. And the upper triangular matrices means that polynomials of degree up to 2 map to polynomials of degree up to 2, and etc. All right, so now what we're going to do is we're going to jump into MATLAB and we're going to implement this code. And we're going to use this to make matrices of our Fourier transform. And then after we do that, we are going to get eigenvalues and eigenvectors for the Fourier transform. And then from that collection of eigenvalues and eigenvectors, we're going to next try to figure out how to orthogonalize them, not with respect to the dot product that you would use in MATLAB, but rather in terms of L2, which is going to be a little bit more complicated.
Now that we have found a way of expressing the Fourier transform of x to the n times Gaussian, let's look at the MATLAB code to put this into a matrix. First, we are going to be using the symbolic toolbox for the symbolic variables. That's what simsx is here for. And what we are going to do is have MATLAB cook up the polynomials we want using a recursive algorithm via this loop here. And we are storing the coefficients of these polynomials in this matrix inside of MATLAB. Now take note, before the loop, we initialize with p equals 1, but since I don't want the double value 1, or floating point value 1, I used x to 0 to tell it that it's 1, but in the symbolic sense. There might actually be a better way to do this, but this is simple enough, and that's just what I do. Now, as far as making the Fourier matrix, we take the coefficients of our polynomial and stuff it into a column of our Fourier matrix. And here we're just taking the one coefficient here and putting it in the top left of the Fourier matrix. And we do this by using the coefficients function, or the coefs function. And this takes the coefficients of a symbolic polynomial and places them into a vector. Two things to note about it though. It puts the leading coefficients first, and second is that if you don't include the all, it will not give you the zero coefficients too. That's why you see all in here, and also that is why I have the code here that is reversing the order of the vectors it spits out. Now the loop itself is really here to recursively change p according to the formula that we determined a minute ago, and then stuffs these coefficients into the Fourier matrix. The recursive formula uses the diff command, or the derivative function for the symbolic functions. I also use square root of minus 1 here because I often have I as an index for loops, and I don't want to confuse that with the imaginary number b. Once we run this code, we get the matrix representation of the Fourier transform on this invariant subspace. And this invariant subspace is determined by our selection of the polynomial degree at the very beginning of the code. And once we use the eigen command, we get an eigendecomposition for the Fourier transform on this invariant subspace. This is nice, but it isn't going to give us the Hermite functions yet. First, we need to use the Gram-Schmidt algorithm to orthogonalize these eigenfunctions. I have the code here, but we should talk about this in a bit more detail on the board first.
Okay, so let's go ahead and talk about what we have so far. Right now, we've taken the Fourier transform, we put it into a matrix into MATLAB. MATLAB then took it and gave us eigenvectors and eigenvalues. The eigenvalues are actually the eigenvalues for the Fourier transform, but the vector space that we're working with isn't Rn. This is just coefficients that should go on to a basis that we have already agreed on. And the basis we agreed on is the x to the n times e to the minus x squared over 2. And so we can go from eigenvectors to eigenfunctions, and this is what we have. So this is all stuff that MATLAB has given us so far. And so we have our eigenvalues, we have our eigenfunctions, but what we really want is we want an orthonormal basis of eigenfunctions. So we can have n eigenfunctions, and that would be a basis of the Pauline's degree n or less, and ultimately a basis for all of L2 if we just take n to infinity. However, we don't have orthogonality yet, and that's not something that MATLAB is going to give us for free. And the reason it's not going to give us that for free is because all of this is just linear algebra. But inner products can change from Hilbert space to Hilbert space, and MATLAB doesn't know what our Hilbert space is. So it doesn't know what the inner product is, so it's not going to spit out a nice orthogonal basis. So that's something we're going to have to cook up ourselves. So what we're going to try to do is we're going to try to go from the collection of eigenfunctions, which you could say is going to be u naught through un, and then we want to spit out this new collection of eigenfunctions that can be v1, v2, up to vn, and etc. as we go off to infinity. So we want this eigenvalue thing to still hold. So we want the Fourier transform on Vj to give us Vj times lambda j. And so that's something we already have with these u's, but we want not only this, but we want this pairwise orthogonality. So if I take the inner product between Vj and Vl, if j is not equal to L, I want this to be 0. I want them to be at 90 degrees to each other with respect to our new inner product. But I also want them to be normalized. So if I have L and j agreeing here, then I want that to give us 1. So what we're going to have to do is we're going to have to use a Gram-Schmidt algorithm in order to make this. I'm going to tell you what the Gram-Schmidt algorithm is in a second. But in order to do the Gram-Schmidt process, what we also need to do is we need to have a nice way of representing the L2 inner product on this basis. And it turns out we can do this exactly without big integrals or anything like that, and I'll walk you through how to do that. And then we're going to cook up what is called a Gram matrix and etc. in order to actually have a nice proper inner product. So let's talk about the Gram-Schmidt algorithm.
Hey, by the way, this video took way too long for me to produce. If you like it, and I can't imagine that you made it this far and you don't, please drop a like and comment below on what you'd like to see next in the series about the Fourier transform. Also, I'm working on a textbook on operator theoretic methods for learning theory and AI, and this is one section that I plan on having in there so that we can lead up to things like reproduce the kernel Hilbert spaces, radial basis functions, etc. But I just want to have a very clear idea on what we mean when we say the Fourier transform and what that's all about. And this stuff with the Fourier transform actually gives us a nice segue into talking about things like dynamic mode decomposition, which I mentioned earlier, and other sort of operator approximation techniques in order to learn some sort of system or approximate a dynamical system or anything else like that. So if you want to see more videos like this, please do subscribe, and you can also follow my Discord, where I'll be posting bits and things like that about the textbook as I develop it. And links for everything you can find in the description here or in the channel about page if you'd like. Anyway, let's go ahead and get back to the topic at hand, which is about finding the Hermite functions using numerical methods for the Fourier transform.
Okay, so now let's go ahead and talk about the Gram-Schmidt algorithm. The Gram-Schmidt algorithm is this. So you take an input of your vectors. So you have vectors u1, say u0, u1 up to un, and the output is v0, v1 up to vn. And what we would like is we would like this inner product to be 1 when J and L agree, and 0 when they don't agree. So these guys are pairwise orthogonal and also normalized. What is this inner product? This inner product is this. So if you have two functions f and g on the real line, if you take their product, where g is conjugated, integrate from minus infinity to infinity, this is the L2 inner product that we were talking about. So in order to do that, what we're going to do is we're going to start with u of 0, and we're going to say v tilde of 0 is equal to u of 0. We're going to come up with this sequence of v tildes first, and then after we're done coming up with these v tildes, which are all going to be pairwise orthogonal, we're going to normalize them to get the v naught through vn. And you want to do the normalization at the end, which is what makes this the modified Gram-Schmidt, because you don't want to have a lot of division happening inside of your algorithms, because that can lead to a lot of floating point errors numerically. So while theoretically it's fine to normalize as you go, in practice, when you're actually implementing this on a machine, you can have a very unstable algorithm through all the divisions. Okay, so we start with this, v naught tilde is equal to u naught. Now I want to make a v1 tilde. v1 tilde, what we need out of this is we need it to be orthogonal to v naught. And when we come up to vn tilde, we need it to be orthogonal to all the guys before it. We're going to take u1, and then we're going to subtract off u1 inner product with v naught tilde, and then we're going to have v naught tilde here, and we're going to divide by v naught tilde inner product. This is a division that we can't avoid. So this is what we end up having. And you'll note that if I were to go ahead and take the inner product between v1 tilde and v naught tilde, then if I expand out v1, well, this guy cancels this guy, and that's u1 v naught tilde minus u1 v naught tilde, and so overall this is 0. So this guy, v1, now we see is orthogonal to v naught, which is really nice. And so you can run this same sort of routine for all the ones we're going to make up. I'm not going to work it out every single time, but that's the idea. Let's go ahead and write down v2 tilde. It's going to be equal to u2 minus, now it's going to be all these terms again. So we have v naught tilde appearing again, and we have the same term here, except instead of u1 we have u2 there. And then we do the same exact thing for v1. So now we have this. And now v2 you can show is going to be orthogonal to v1 and v naught. And in general, if you want to take this up to, say, vn tilde, it's going to be un minus the sum of un against vj tilde divided by vj tilde times vj tilde. And that is j going from 1 up to n minus 1. And so there we go. This is the Gram-Schmidt algorithm, except we haven't normalized yet. Everything is pairwise orthogonal. And so the last step here then is we say that vj is equal to vj tilde divided by the square root of vj tilde. Then that gives us everything we need. There's some things we need to say about this. First, given this u naught to un, it does give us this orthonormal set of v naught through vn, which is really nice. But something you might notice is that we haven't said anything about the Fourier transform through here or the operator that these guys apparently diagonalize. Now, usually what you do when you're talking about producing an orthonormal eigenbasis, what you have to do is you have to do this whole Gram-Schmidt process individually for every single eigenspace. There's an exception where you don't have to worry about that, and that's when your eigenspaces for your operator are all pairwise orthogonal. So that means that if you take any vector that corresponds to an eigenvector for, say, 1 versus any eigenvector of I, then those two will always be orthogonal. Then you can just spit out this for using your eigenbasis that you found, and then spit out an orthonormal eigenbasis. And that's what we're going to end up doing. Now, we don't have guarantees that these are always going to be orthogonal, except the fact that we already know that they are on the other side of it. But there's usually two different kinds of operators that will lend themselves to this. So first of all, if your operator is self-adjoint, then if you have vectors corresponding to different eigenspaces, then you know that they're actually going to be orthogonal to each other, which is really nice. The Fourier transform isn't actually self-adjoint, though. It is unitary.
Let's talk about unitary operators real quick. L2 is a Hilbert space, and as a Hilbert space, it has an inner product. The Fourier transform is a bounded operator on L2, and as such, there is a unique adjoint operator that is essentially the movement of the Fourier transform from one side of the inner product to the other. So the inner product of the Fourier transform of f with g is the same as an inner product of f with the adjoint of the Fourier transform against g. Now, every bounded operator has an adjoint like this. However, in this case, the adjoint of the Fourier transform is also its inverse, and this makes the Fourier transform a unitary operator. The eigenfunctions for the inverse operator are actually the same as the eigenfunctions for the original operator. And so in this case, the Fourier transform and the inverse Fourier transform have the same eigenfunctions. The eigenvalues do change, but the new eigenvalues for the inverse operator are actually the inverses or the reciprocals of the eigenvalues of the original operator. Using this, we can come up with a nice formula expressing the orthogonality of the eigenfunctions for different eigenvalues. Let's say f and g are eigenvectors corresponding to different eigenvalues lambda and mu. To see this property I want to express, we actually replace f star with f inverse in that inner product we showed earlier, and then we use the eigenfunction property. A bit of linear algebra and moving everything to left and right gets us this. Lambda minus 1 over bar mu times f inner product with g is equal to 0. The bar came from the fact that if you take a scalar out of the second entry in your inner product, it comes out as a complex conjugate, and of course is reciprocated, or is 1 over bar mu, because f star became f inverse. This tells us that either lambda is equal to 1 over bar mu, or that f inner product with g is equal to 0. Since the only eigenvalues for the Fourier transform are plus and minus 1 and plus and minus I, we can actually quickly see that lambda is actually not equal to 1 over bar mu for any combination of eigenvalues. Hence, f and g are orthogonal if they correspond to different eigenvalues. This means we don't have to worry about breaking orthogonality if we run the Gram-Schmidt process altogether, and so we don't have to segregate everything into being eigenvectors for 1 and minus 1 and minus I and plus I. We can just do it all at once, and there's no danger of interference between these because they are pairwise orthogonal already.
Okay, so what we saw from the Gram-Schmidt algorithm is that in order to implement it, we have to go through and we have to compute a lot of inner products, and these inner products are coming from our Hilbert space. Now, the Hilbert space inner product for us is f inner product with g. These are two functions of a real variable, and it's the integral from minus infinity to infinity of f of x times g of x bar dx. Right? So this is the inner product, but I'm going to show you how to take the inner product not by doing this, but by using the coefficients of our against our basis. So here we have two vectors v and u, and I want to compute the inner product between v and u. Now I could just go ahead and express them here like this, just the sum of aj times ej at x, bj times ej at x, take and then take the product, conjugate this guy, integrate minus infinity to infinity. I can implement it in MATLAB. I can use something like Simpson's rule, and ta-da, I have an inner product, and I don't have to know anything about anything, and that's fine. Except if I use Simpson's rule, then I introduce some numerical errors, and those could accumulate over time, especially if we have to do a lot of divisions and other things. So we want to minimize errors as much as we can. So I want to come up with another way of doing this. And so what I'm going to do is I'm going to show you how you can start from these guys and use just the coefficients from u, so there's b naught through bn and the a naught through an of v, and I'm going to express this guy as an inner product that you can compute with just matrices, and it'll show us some very particular inner products that we need to go and separately work out, and so that'll come next. What I'm going to do here is I'm just going to use the linearity properties here. So I have a naught times e naught, and adding that up to an times en, and we're going to have the inner product, we're going to b naught e naught up to bn en, right? And so when I do this, I can go ahead and first just go ahead and write this, expand this out, and use linearity here. And so this is going to be the same as a sum of aj times the inner product of ej against these guys, b naught, e naught, up to bn, en. And this is j, of course, running from, say, 0 up to n. Okay, so now I can do the same thing in here. Okay, so j equals 0 to n of aj against, now we have another sum, and this is, I'll put in terms of L going from 0 up to n. It's going to be BL. Now we're going to have EJ here, and this is going to be EL. Boom. And so then this sum doesn't depend, these sums are sort of independent of each other, so I can just go ahead and move that sum all the way out. And so we're going to have the sum over J, the sum over L. I'll suppress the actual indices. We have, oh, and this should have come with a conjugate. Sorry about that. So we're going to have AJ times BL conjugate times EJ against EL. But I would like to express this in terms of something that's easy to put into MATLAB. Running these sums is going to be a double for loop in here, and you know that's not fast in terms of MATLAB. You want to turn everything to be vectorized. Yep. And so what you'll notice is that we can actually go ahead and rewrite this in terms of vectors and matrices, and in terms of a vector of a naught through an. And you can run a comparison here. It'll just take a minute. But basically, this is going to be, say, b naught through bn. I'm going to put a dagger here. And for dagger, I mean the conjugate transpose. So we'll say that, say, b naught through bn dagger is equal to, say, b naught bar up to bn bar, right? That's what this is. So this is a pretty typical notation, comes out of physics and quantum mechanics. So here, then we're going to have these guys is called a gram matrix. So it's e naught up through, say, e naught en, and this one down to en e naught, and this over here to en So this is a self-adjoint matrix. And then we're going to have this guy times a naught down to an. And there we go. So this ends up being a nice and easy way for MATLAB to take a vector that you have out of here, and so these coefficients are things that we have spat out directly from our matrix routine in our eigenvector routine that we put into MATLAB. And so in order to figure out the inner product between functions like this represented as vectors, we just need to make sure we insert these guys. And so now I need to figure out what these inner products are, and then once we do that, we're golden. Let's go ahead and do that, and it'll be the last step before we can finish off our code for the Fourier transform, for discovering the Hermite functions through the Fourier transform, which is becoming bigger than I expected it to be. All right, so here's where we're at. We want to figure out the inner product between EJ and EL, and once we figure this out, we can finally wrap up our Gram-Schmidt algorithm and code it up, and everything will be fine. And so EJ and EL, well, these are basis elements where we have, say, En is equal to x to the n times e to the minus x squared over 2. If we take the inner product in L2, then this is what it gives us. The x to the j and x to the l end up combining to give us x to the j plus l, and the e to the minus x squared over 2 times e to the minus x squared over 2 basically just gives us e to the minus x squared. So we need to take this guy, we need to figure out what this is. In order to do that, we're going to just first define In as being the integral from minus infinity to infinity of x to the n times e to the minus x squared. And now we have two cases. One case is trivial, and one case we're going to have to end up having some sort of recursion and induction argument for this. The really easy case is n odd. Then x to the n times e to the minus x squared dx. This is integrated from minus infinity to infinity. This is an odd function because e to the minus x squared is an even function. Even function times odd function is an odd function, and so we get 0. And that's just because we have a function like this, right? So all the positive values are canceled out exactly with the negative values, and so boom, gives us 0. Okay. So the more complicated part is when n is even. And so in order to figure out this problem, what we're going to do is we're just going to use integration by parts. Integration by parts is going to allow us to express in terms of in minus 2. And then we can go ahead and work from there. Doing integration by parts, what I'm going to do is I'm going to take off one of these x's, I'm going to leave it with this guy. So my dv is actually just going to be x times e to the minus x squared. And my u then is going to be x to the n minus 1. Now, if I take du, then that's going to give me this. Du is equal to n minus 1 times x to the n minus 2. And v here is then just going to become minus e to the x squared minus x squared divided by 2. All right, so now using integration by parts, I get u times v. So I'm going to have x to the n minus 1 times, x to the n minus 1 times minus e to the minus x squared divided by 2. This integrates minus infinity to infinity. Now, this, I didn't really have to write this down because this is just a monomial times a Gaussian that is going to 0 really, really fast. So towards minus infinity, this goes 0. Towards plus infinity, this goes 0. So altogether, it just disappears. So now I have minus the integral of v du. Minus, and here it turns into a plus, so it becomes the integral from negative infinity to infinity. We're going to have v, which is going to give us 1/2 times e to the minus x squared. And we have our du, which is n minus 1 times x to the n minus 2 dx. And rewriting this, we end up getting n minus 1 divided by 2 times the integral from minus infinity to infinity of x to the n minus 2 e to the minus x squared dx. Or is n minus 1 divided by 2 I sub n minus 2. And so then what we can see is that if I have an even number n, this is going to be n minus 1 divided by 2, and then this guy, I can rewrite this as going to be n minus 3 divided by 2 times the next one, all the way down until I get to, say, 3 times 1, each of these divided by 2, and then times I of 0. And so, using an induction argument, we can spit this out, and I of 0 is just the square root of pi. Because this is I of 0. Now, what I'm going to do is I can go ahead and rewrite this as a double factorial. So it's n minus 1. And we call this double factorial where you skip 1 every single time. And then at the bottom, we have a whole bunch of 2's. How many 2's do we have? Well, we have n over 2 of them. So we have 2 to the n over 2. And we don't have 2 to the n because we skip 1 every time, right? And then this guy times pi. So in the even case, we're going to end up having this. So more concisely, I guess I can write this over here. We have our inner product with EJ and EL then is equal to 0 if J plus L is odd, and otherwise is J plus L minus 1 double factorial divided by 2 to the J plus L divided by 2. And this times square root of pi, and this is J plus L is even. Okay. Now with that, I think I'm done here at the board, and we can finally finish writing up our code. So let's go ahead and take a look at the code that I put together, and we'll wrap this up. Oof. I'm so tired.
Okay, so I'm over here in MATLAB now. And so this is code. This is the entirety of the code that we need. It's not all that long. It's about 63 lines, and then I have 2 other functions called inner product and norm of basis. And all of those all together really aren't all that long. So let's go ahead and start off. And so I'm going to show you the symbolic package. And so we see that here the code starts with sims x. So I made a symbolic variable, which is invoking the symbolic toolbox inside of MATLAB. Then once you have this, you can do things like this. So I'm going to say y is equal to x squared plus x. And then that gives me x squared plus x. But that's not all that significant. But what's really cool is I can do this. I can go ahead and write diff y, and it gives me a derivative. So I can now use the symbolic toolbox and a few commands in MATLAB to do basic calculus, which is pretty interesting. So now, in order to make the matrix that we want to make, we have a recursion on the polynomials. We know that the new polynomial is going to be an operation on the old polynomial, where we multiply times I and also by the derivative of p minus x times p. And that should give us it. So I'm going to go ahead and instead say now y is equal to x, or well, actually y is equal to x to 0. So now we have a symbolic variable 1. If I would just put y is equal to 1, it'll think 1's a double. So we have to be careful with that. Y is equal to the square root of minus 1 times the derivative of y minus x times y. And that should give me my new function. So if I do this, it gives me minus I times x. And if I do it again, it gives me 1 minus x squared, which is what we saw. And then I do it again, we get this guy. Can I do more? I could say expand y, so on. There we go. That's more comfortable. Okay, so now something else I can do is I can also pull coefficients out of a polynomial. So this is cos y, and so I end up getting this. But notice that it's only giving me 2 coefficients, which is kind of weird because this is a cubic polynomial. So if you want all of them, then you need to add in all. And you see I did that in the code above. And so then it gives me this. And so the leading coefficient here is this guy. And then this is my constant coefficient. Often I kind of want to have my constants at the very top, at the very beginning, and the higher ones later. So what I can do is I can say answer n to -1 to 1, and it should flip it around. There you go. Okay, so then this is ultimately going to be what I put into one of my columns. So I can just go answer point. So I put a period here so it doesn't conjugate, and so it just gives me a straight transpose. If I put this would be like dagger notation. So then that's a column of my matrix. And so then I go ahead and I do this several times over, and to whatever degree I choose. So here I'm going to go ahead and make my Fourier matrix, and I'm going to keep this to degree 15. So it's going to be, should give me like a 15 by 15 or 16 by 16 matrix. Well, let's just change it to 3. So we see what we saw on the board. And so let's evaluate this Fourier matrix. There we go. So we have 1 and then 0, 0, 0. Then here we have -I and 0, 0. And here we have 1 and -I for these coefficients. And then finally, -3I and I here. So this is a diagonal matrix, and this first diagonal is going to just be a 1. Then we have a -1, or a -I, -1 times I. Then we have a -1, and then we have a 1 here, all in the diagonal. And since this is an upper triangular matrix, these are indeed the eigenvalues of the Fourier transform. Okay, so this is how I'm making the Fourier matrix. And so this is the matrix representation. Once I have this representation, that means I can now go into MATLAB and just put in this guy, the eigenfunction, on the Fourier matrix. And so it's going to give me 2 matrices. It's going to give me V, which is going to be, each column is going to be an eigenvector, and D, which is a diagonal matrix having my eigenvalues. Let's go ahead and evaluate this. Boom. And so then if I go ahead and take a look at V, we already saw that this guy, which corresponds to the Gaussian, is an eigenfunction for the Fourier transform. That's good. And this one, x times Gaussian, is also an eigenfunction for the Fourier transform. And then we have 2 other eigenfunctions here. But then if I take a look at D, it's a diagonal matrix, so I'm just going to extract the diagonal from it. It's the only information that's important. And these are my eigenvalues, 1, -I, -1, and I. And so that's exactly what we saw on the board, and so that's good so far. So now the next step is to do the Gram-Schmidt process. So the next thing we need to do is we need to do the Gram-Schmidt process to take these eigenvectors and their corresponding eigenfunctions, and we want to spit out an orthonormal basis of eigenfunctions for the Fourier transform. We have here, this V2 is going to be the set of orthogonal eigenvectors that we have throughout this process. And right now I just set it as a bunch of zeros, the same size as this matrix V. V is our set of eigenvectors that we found numerically. Then basically what we're going to do is we are going to go ahead and do the orthogonalization process. So the first thing we do is we set V2 is equal to V1. We're not going to normalize yet. So then I have this V2 hold, which is just this guy. So here we have a loop where we're going to take each of our new vectors and we're going to subtract off inner products times the old vectors to make sure that everything ends up being orthogonal to each other. After we do all that stuff, then we go ahead and update the matrix and we put the new vector that we just found inside of there. And so this goes through, and once we're done with this loop here, we have a collection of columns that are orthogonal with respect to our L2 inner product. I haven't shown you the inner product code yet, but we'll get to that. Then at the end, we go ahead and we normalize by dividing each one of these vectors by the square root of the inner product of these two guys. All right, so that's Gram-Schmidt. Now I want to take you through these two other bits of code and everything will be explained. And so we have the inner product. The inner product, again, is going to be using the expansion of these vectors, these eigenfunctions, in terms of the other basis, which means that the inner product for these vectors comes down to the inner product between these two different basis functions. Essentially, I have my Gram matrix, IIJJ. This is the Gram matrix, the matrix that has all of our inner products of our basis elements. And so we make this matrix, and each element of these is going to be an inner product. And this is that I vector that I was the IN term that we did on the board. Y ends up being this, so it is V2 prime, where the V2 was our input up here, and V1, which was our input over here. So notice that V2 gets conjugated because we didn't put a period here, and that's important. So anyway, and then we have the Gram matrix on the inside, and ta-da, there we go. That's the inner product. So we just go ahead and return this as our output Y. Last thing to do is talk about the norm of the basis, norm basis function. And so this one is just that IN thing. So basically if n ends up being odd, we just say y is equal to 0. This is x to the n times the Gaussian, remember. And then here we have hold n minus 1. And so in here, I just make up a double factorial algorithm really quick. It runs through and does this. And then we have the square root of pi times the double factorial. And again, I'm saving the division here so we don't have issues with floating point. I think actually dividing by 2's is actually not quite so bad floating point wise, because it just sort of shifts things bit wise, but I just prefer to be cautious about this. So in any case, that's that. And so with all of this together, we have this guy gives us the inner products between two basis elements, and that feeds into this Gram matrix, which gives us this way of taking an inner product between the functions that are represented as linear combinations of this basis, and then this is fed into here in our Gram-Schmidt process, here, here, and in here. The first two times was for orthogonalization, and this time is for normalization. And then with all of that, then we get Hermite functions, presumably. So what I'm going to do then is I'm going to go through and I'm going to show you a couple of Hermite functions, and we're going to come back to this code, and I'm going to show you how this gives us Hermite functions back. So let's go and look at my Hermite generator code here. This one, I think if I remember right, this is off by 1 error. So if I go ahead and say degree 1, let's go ahead and take a look at my first Hermite functions. Let's run this. What does it give us? Let the code run for a second. There we go. Okay. So yeah, so this is off by 1. This is actually my 0th Hermite function. And so you see it's just the Gaussian, nothing really too crazy here. But then if I go ahead and I change this to be 5, so this would be my degree 4 Hermite function, we end up getting this. So it's a nice even function here, and we have 1, 2, 3 peaks and 2 troughs. And so that's kind of what we're looking for out of our new code as well. So this way of finding Hermite functions actually uses what's called Rodriguez's formula. And so this is different than, say, what I'm doing with numerically here with the Fourier transform. What I'm going to do is I'm going to show you that this is going to give me the same functions that I get out of this. So for my 4th degree polynomial, let's see if this gives me what I want. All right, so here we have almost exactly what we wanted, except everything's sort of flipped upside down. So we have 1, 2, 3 troughs and 1, 2 peaks, but it's basically the same function. It's just, we're in a vector space, so we can just put a -1 on that and flip it around. It's fine. Okay, so that's good. Okay, so this is a proper 1st degree Hermite function. And if I put in 0, there we go. We get the straight Gaussian. That's what I expected. That is the 0th degree Hermite function. And let's see something a little bit more exciting. Let's take a look at the 10th one. And so if I go ahead and push play on this, boom, there we go. We get a whole bunch of wiggles here. And I think it's really interesting with all these Hermite functions is they look really a lot like sinusoids inside of some sort of small region, and then suddenly they just sort of die when they go off to infinity. That's Hermite functions. There you go. And this is the 15th one. So okay, yeah. So these are the Hermite functions, and we have just discovered them numerically. This was a lot of effort, and if you like this sort of video and you've stuck around this long, then please, give me a like and subscribe. I like making functional analysis content, numerical analysis, data science, that sort of stuff. I am a functional analyst, and I'm writing a textbook on functional analysis, and I'll put some updates on here and also in my Discord, which you can find a link down below. In any case, thank you so much for watching. I think I'm done, and yeah, have a great day.